pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
He has done research. The reason the fossil site out there, the reason they hired him was because he's such an expert on mastodons. He's done all kinds of research on dogs, bison, just all types. Mammoth Cave. He's done lots of research in Mammoth Cave and all over the Midwest. So, no more thing. His name is Swedish. So let's give him a big hand and encourage him in his talk.
It's good to be here today. This is a great crowd for a Monday morning, I have to say. I've kind of had a circuitous route to get here in front of you today. An abbreviated music career into archaeology and anthropology. My PhD's actually in anthropology, which is kind of strange for a vertebrate paleontologist. But I spent the last 8 years at the Illinois State Museum before coming here as curator of geology, and really worked a lot on mammoths and mastodons. They're kind of key in the Midwest, and looking up there, we look at their extinction because 12,000 years ago, 20,000 years ago, most of the Midwest was covered by ice, so most of our record has been obliterated. That's older than 20,000 years. And so the record that we have is this very tiny little window between about 20,000 years and 12,000 years. And so we're always very interested in how they went extinct, which is one of the big questions that we try and ask. Of course, towards the end of my tenure at the Illinois State Museum, the director of the Great Fossil Site down here, Blaine Schubert, who was once a research associate at the Illinois State Museum, sent us an email and knew that we were very interested in mastodons, and sent us an email with a picture attached. It was a picture of a mastodon tooth. And he says, "Is this a mastodon?" We emailed back and said, "Yes, of course, you know this. You know what a mastodon looks like too." It's like, good. This comes from the Great Fossil Site. So we looked at it and didn't really have anything else to add. It just looked like a big molar of a mastodon. And we see dozens, if not hundreds of those through the last couple of years. And the record in the Midwest is really rich in mastodons. But they all date to that tiny little time window that is about 12,000 to 20,000 years ago. Great Fossil Site is 5 million years old. So this was something that it's a mastodon tooth that looked exactly like the things that we were finding that were much, much, much younger. And so fast forward a couple of years, and I'm here. I've been here for about a year and a half, and was hired as head curator at the Great Fossil Site. And we love it. We like the topography. We love the warmer winters. And the people are wonderful. But the fossil site is also fantastic. I mean, this is one of the things that is something that is truly unique, not just at kind of a local or a regional scale, but really at a global scale. The paleontological record that we have at the Great Fossil Site is something that you won't find almost anywhere else in the world. So today I'm just going to talk about one species of over 100 species that we've uncovered at the Great Fossil Site. It's the biggest of these species, and it's the one that I know the most about. But we'll dive into this, and so I'm going to talk about mastodons from the Great Fossil Site. Let's see if I got my clicker. To just kind of remind you guys, a lot of you have been here longer than I have, obviously, so it always helps to kind of just review a little bit of the discovery of this. And some of you may remember this, some of you may have been around at this time. This is what the Great Fossil Site looked like when it was first discovered. This is the highway that goes right by Daniel Boone High School, and Daniel Boone High School is right over here, and this is Fulkerson Road, and this is a hill. It's kind of hard to see in this picture, but this is a pretty good-sized hill. Fulkerson Road came over this hill, and then it was a very steep kind of drop back down to a stop sign right in front of the highway. And it was a dangerous intersection because people would fly over this hill, they would see the stop sign, it would be too late. And so TDOT looked at this dangerous intersection, they said, okay, we have to do something about this. Being engineers, they said, let's remove the hill. So that's what they started to do here, and that's why you see all this exposed dirt. They started grading it down to make it less of a hill, to improve visibility and that sort of thing. And they kept going until they hit this black clay. So this is a layer within this hill that is a black clay, and this stood out as something really different because most of the dirt that we have around here is this bright red stuff. What we see here is actually, this is stream deposits that are on top. This is the Ford Creek Valley. And over the millions of years, over the last 5 million years, the Ford Creek Valley has been eroding away at the landscape around it. However, this black stuff is a really thick clay, really dense clay, and it's erosion resistant. So it means that when the Ford Creek Valley hit this hill, it couldn't erode it away, or it didn't erode as much of it away as the surrounding sediment. And so it remained. And so this is actually a plug of a sinkhole fill. So what we're looking at the Great Fossil Site is a collapsed sinkhole. So we know all about sinkholes in East Tennessee. And it's a collapsed sinkhole. It filled with water, and then over thousands of years, we think it's probably thousands, not millions, over thousands of years, filled with sediment, fine-grained sediment. And in those sediments, you also had animals dying occasionally. Over thousands of years, you can get hundreds of animals, if not thousands of animals that are attracted to a water hole. And they may be sick, they may be old, they may be young, they may be in the prime of their life, but for whatever reason, they end up trapped in that sinkhole. And this is what this gray clay represents. And this is basically the fill of that collapsed sinkhole. All the surrounding limestone has actually eroded away, and the only thing left is the clay fill. To kind of zoom forward a little bit, since 2000, there's been a lot of work at the site, obviously. Some of you have contributed to that work at the site. I see some volunteers in the audience. And since that time, up here I have 93 vertebrate species. Actually, we're over 100 now. I think at last count we were at 104. As of 2 weeks ago, a couple of our paleontologists published on a wolverine from the site, which was truly bizarre. Most wolverines we think of as northern animals. This particular wolverine was hanging out with alligators. It was warm. They named it a new species, Gulo. I can't remember what the Latin species name is, but the translation is sweaty glutton. But this particular wolverine, it's 1 million years older than any other wolverine in the world. So it's really changing how we think about wolverines. We used to think, well, okay, they must be this northern species, they're northern adapted. They adapted where it's cold. This is the earliest one, and it's down here where it's obviously very warm. Not based on our concept of what the climate is today, but based on the concept of the climate that is represented in the site. We have alligators there. We have big turtles that don't like it cold. We have other species that won't handle cold winters very well. So we're constantly discovering some of these new species. So that's why I say and growing, and that's one of the things that we try and convey, and we're going to try and convey more often at the fossil site in our exhibits and in our programming, is that we're not done. We're constantly learning, and this is science. Science isn't a collection of facts. Science is a process. Science is a way of understanding the world, and it's a methodological way of understanding the world. And we want our visitors to walk out the door knowing that we're not done yet, knowing that there are still questions to be asked and answers to be made. So this is kind of key. We have over 20,000 catalog specimens since we started excavation. I think the last count was about 24,000 specimens, so individual bones that have entered into our collections. That is huge. We add 2,000 to 4,000 specimens a year. In my 8 years at the Illinois State Museum as a curator of geology, I counted it a good year if I added a couple of dozen specimens. So, and this is that's a good mid-sized museum. 2,000 to 4,000 specimens a year is, frankly, an insane amount. you see this in like the really big museums, like the American Museum or the Field Museum or the Smithsonian. They may be adding, 2,000 to 4,000 specimens a year, but not a small museum in East Tennessee. So this is part of the reason why I say we're still growing, we're still learning, we're still doing stuff, and it's going to be a while before we really have answered even a few of the questions that we're starting to pose right now. We've answered a lot in the last 20 years, but we're still asking a lot too. It's really a neat part of our museum is that we have such an active volunteer program, and we cannot do what we do without the volunteers that we have. We have a staff of 7. That's 7 staff. We have over 100 volunteers, some of them are out here, who show up every week to do a lot of the heavy lifting of the sorting through matrix to identify small bones, the prepping and the cleaning of specimens that come in out of the field. They work in our collections. They do all the things that need to be done. And so this is one of those things that is really, I consider it really a gold star for our museum. And it's something I don't see at other museums. I've been around a lot of other museums. You're lucky if you get, a half a dozen people who show up regularly and help out. But these guys, they do it every day, and they're there, and they contribute in really substantial ways. In 2016, we entered into a partnership with the Hands-On Regional Museum. And this is something that we think it's going to be really good over the long run. We have a very complementary philosophy in terms of our approach to science, our approach to education. Hands-On really wants children and kids and families and their visitors to learn through doing, to understand the concepts behind science. So they're adding, even this summer, they have a grand opening for their exhibits out at the Great Fossil Site. They're filling our temporary exhibit space in our annex with modular STEM exhibits, science, technology, engineering exhibits, and so we think that that's going to be a really good partnership over the long run. We're also collaborating on our kind of crossover exhibits that do both. For instance, there will be a climbing exhibit in our central lobby. It will be installed in September. And I jokingly like to refer to it as a $300,000 piece of paleontological sculpture that you can climb through. So it will be a kind of a climbing exhibit for kids, but they're using 3D models of our fossils. And they're 3D printing those models. They're inserting them into the exhibit so kids can actually experience them up close. They can handle them. They can touch them. They can see how big our mastodon jaw is because they can lay down next to it. That sort of thing. So this will be really fun in the next couple of years. Ultimately, our goal is to be a regional center for science, natural history, and paleontology in East Tennessee. This is a niche that is not very well filled in Tennessee right now, and so we are definitely filling it, and we're moving more statewide. But this is just to kind of give you some background. That's not why I'm here today. I'm here today to talk about mastodons. But before I talk about mastodons, I kind of have to talk a little bit about how we know how old the Great Fossil Site is. This is coming from we can't date it. So a lot of you may have heard of things like radiocarbon dating. Unfortunately, radiocarbon dating, all of your radiocarbon is gone. Your radiogenic Carbon-14 is gone after 50,000 years. And so if you have a site that's older than 50,000 years, you can't date it using that technique. You have to use a different technique. There's a couple of new dating techniques that we're exploring, especially this summer, looking at isotopes of things like aluminum and beryllium. So some really weird kinds of chemistry going on. But before that happens, we have to look at the species. That's really how we know how old this site is. And so what we can do is we can look at the species that are dated in other places. They have volcanic ashes that we can date out in Oregon or Washington or out in the western US. We look at some of these species. These are all Latin names of some of the species that we have at Gray. So for instance, Arctomeles is our badger, Teleoceras is our rhino, this is our horse, Milohyas is a peccary. So these are the species that we have that we've excavated from Gray. And we can take each one of these and look at where it occurs elsewhere in North America and what it dates to, and we can plot that. And then where they overlap is what our age range is. This is a technique called biostratigraphy. And the more species you add into this mix, the tighter your age range. And so Josh Samuels, who's a very recent hire at ETSU, new paleontologist there, his specialty is small animals. And he's coming from Oregon, where he was doing a lot of this sort of thing. And so this is a graph that he put together a couple of months ago, and looking at all these species and how they line up. And he came up with a new estimate for the age of the site, which is 4.9 to 4.7 million years ago. Super tight age range for something that is about 5 million years old. So we can start saying, okay, we can start hanging our hat in terms of time on how old the great fossil site is and what else is going on during that time. This is a map of kind of similar age sites throughout the U.S. And this is their distribution. We have a couple of sites down here in Florida, kind of into the middle of the country, and a lot of sites out here in the Great Plains, but then also a few out here in the western U.S. And you can see the Great Fossil Site is not in that yellow band. So that's part of the reason why it's so interesting, is because it's in a place, it's in an ecosystem, it's on a landscape that is not represented anywhere else in the fossil record. The fossil record is kind of funny. Not everything preserves everywhere in the same way. So I mentioned in the beginning that in Illinois, in the Midwest, we had this very tiny window that most of our fossils dated to because we had glaciers come through and basically obliterate everything on the surface. And it's a similar thing going on in most of the eastern U.S., where you have basically erosion happening and removing a lot of the old sites and regularly removing a lot of sites. It just so happens that the Great Fossil Site is this little niche of sediment, of dirt, that avoided most geologic processes that would obliterate it. And so we lucked out. But this means that there's a lot of kind of strange things, strange in comparison to the rest of North America. We're probably wetter. We may or may not have forest fires or seasonal fires. So we would expect to see kind of a different kind of landscape here. We think it's probably forested. We base that on pollen and some of the plant remains that we see in the fossil deposit. But in the end, it's not something that is easy to compare to the rest of the fossil record, which is from these other places. Which means that we get strange animals. Red panda being one of the strangest. So before the Great Fossil Site red panda find, there was one locality in North America from Washington State that had a red panda in it, and it had a single tooth of a red panda. We now, at last count, I think was 5 or 6 red pandas, individuals. We have 2 or 3 that are fairly complete skeletons. So we're talking probably almost 1,000 bones of red panda from the Great Fossil Site. This is a beaded lizard. This is kind of a strange thing. The beaded lizard that most of us are probably familiar with is the Gila monster. It's a southwestern lizard, and we've got a relative of it here at the Great Fossil Site. So we end up with these kind of strange species here in East Tennessee that we don't expect. They're here 5 million years ago. And one of these species, we knew this early on. We get rhinos. I mean, who expects rhinos in East Tennessee either? But we knew early on that we had an elephant. We just didn't know which one. This is from this. There was a little tiny chunk of this is a tusk of an elephant, and there's a little tiny chunk that was found, ivory from this tusk, that was part of the initial discovery. As the bulldozers were grading Fulkerson Road, some of this ivory came out, and our field director, Sean Hogred, went back in 2015 and started. He knew where that had come from, kind of roughly, and went back in 2015 and started following, kind of going on each side, seeing if he could find more of this particular tusk. And he found more. So he found bigger chunks here, bigger chunks there. There's a missing segment that was damaged during road construction, but he was able to find more of it. We're not sure, tusks in and of themselves are not particularly diagnostic to species. We can't say whether it's a mammoth or a mastodon. We had 3 options in North America. We had 3 different kinds of elephants that made it here. There are mastodons, so this guy. There are mammoths, which are really familiar, and there are gomphotheres. Gomphotheres are what we would say are like the shovel tuskers. Sometimes you see them in Florida, you see them out in the Great Plains, but they have very strange lower tusks. And so the mastodons and gomphotheres were both here very early. They were both here before 10 million years ago, came in around 14 million. Mammoths are really recent migrants. So they only got here about 1.5 million years ago. So we had 2 options. The mammoths got here too late to be the owner of that tusk. But it could be a mastodon or it could be a gomphothere. And initially we thought, let's see, there we go. Initially we thought it was a gomphothere. So when we designed the exhibits in the fossil site, we thought it was a gomphothere because there were other gomphotheres around in Florida, there were gomphotheres in Alabama. We thought, okay, it's not a big jump to expect them in Tennessee too. But all we had were some of those tusk fragments and a couple of foot elements, just some bits of their feet, and some bits of their ankles. And so that's what we designed our murals. So if any of you have been out to the fossil site, this is one of our murals with this gomphothere. So you can kind of see it has these shovel-shaped incisors, shovel-shaped lower tusks. They're very distinctive for gomphothere. But their teeth are also really distinctive. This is the top-down view of one of their teeth. This is probably about the shape and size of maybe a small football. And so it's a big teeth. This is its wisdom tooth. So it's its last molar. And they're very distinctive in that they kind of have, they're these loaves that are crosswise, and then they have these little kind of middle parts that would increase their grinding area. Mastodons, on the other hand, they look similar, but they're not the same. So you notice they lack those middle pieces of enamel that the gomphotheres have. And so that is really what we were looking for in terms of what kind of an elephant we had here. And this is actually the tooth that we have from the Great Fossil Site. So it's definitely one of these, the true mastodons, rather than the gomphothere, which are also called sometimes the false mastodons. Which makes it kind of interesting. I'm a paleontologist, so I have to talk a little bit about how elephants, how mastodons actually kind of take over North America. The mid-Miocene is, we're talking about 10 million years ago. And so this is our traditional idea of mastodons in North America, is that we have a couple of species that come over, Myomastodon. It's a very creative name, Miocene and Mastodon. And so we think that they're here during the mid-Miocene. During the Pliocene, which starts about 5 million years ago, It goes up to 2.5 million years ago. We call it Pliomastodon. And we think that these things kind of just turned into each other. And then during the Pleistocene, during the Ice Age, you end up with the American mastodon, also the name mammoth. That's the Latin name for the American mastodon. And that's what we see in the Ice Age. But one of the things that we're thinking is going on because of Gray. 5 million years ago, we have a tooth that looks just like, we can't tell the difference between the tooth that is, let's see here, this old and this old. That we call that very morphologically conservative. So it means that the tooth doesn't change a whole lot through time. There are other parts of that body shape and size that do, but in this case, the tooth isn't changing a lot over time. And so what we're finding is that there's probably really two species that come across the Bering Land Bridge into North America about 10 million, between 10 million and 15 million years ago, and one of them dies out. Zygolephodon goes away, and this one, we know that because it has very, very different teeth. Mastodons are here all the way through. And the gray fossil site mastodon is kind of a key middle part of this story. So I won't talk a lot more about that, but that's one of the directions where the research is going. As paleontologists, we're used to dealing with a very fragmentary record. We're lucky if a single bone is complete, let alone getting more than one bone of an individual. That's the way the fossil record works. It's really hard on fossils. But so far, we have excavated from at least our largest mastodon. We've excavated the skull, the jaw, most of that tusk, which I already showed you, some of the backbones, the shoulder blades, all 4 legs. In fact, one leg is jacketed up in a plaster jacket in our lab right now. We wrapped it up and took it down to the Johnson City Medical Center so we could get CT scans of it. Its wrist is all articulated, which is really rare with elephants. Because if you look at this is kind of interesting. This is a multi-ton animal, and they actually walk on their toes. They have a big fat pad underneath their foot that takes most of the weight. And so those articulations are not really tight. If those bones came out of the ground one at a time, we wouldn't be able to really tease apart how they go together and whether this foot was really on their toes or whether it was kind of halfway on its toes or whether it's a little flatter. And so we can't really see that in the fossil record, but we can at Gray because this particular mastodon is articulated. And so that was why we took that jacket down to the Johnson City Medical Center to get CT scans, because we wanted to see what that wrist looked like. We wanted to see what that foot looked like before we started taking the bones out, stabilizing them, preparing them, and that sort of thing. So this is some of the things that we can tell about this particular animal. We have even its tail vertebrae. So it's very, very complete. And this is really, really fun for me as a mastodon paleontologist. But, as an elephant paleontologist, as a person who thinks about elephants, everybody always asks, how big was it? That always is what comes back to it. And here you can see this is a modern elephant ulna. So this is a bone of its front arm. And you can see this is from about a 15-year-old female, not a really big elephant, but it's elephant sized. This one is our ulna from our mastodon in the field. So you can kind of see this is the notch here, corresponds to that notch there. This is the proximal end, it corresponds to that proximal end. Distal end up to here. You just see how massive it is. And we can use that. We can use those long bones to calculate kind of precisely how big it was. We can look at shoulder height. So with height up to about here. We can look at body mass. And so we plug those things into an equation, and we end up with, actually I don't think I have the slide. we end up with a shoulder height of about 13 and a half or 14 feet. We end up with a body mass of about 16 tons. So we've affectionately started calling this particular animal Ernie, after Tennessee Ernie Ford. Yeah. So that when you spend this much time with this kind of an animal, they have to have a name, and this one had an obvious name. So yeah, 16 tons. To kind of put that into perspective, our gray fossil site animal, in comparison to some of the largest elephants that are around today, the largest African bush elephant is about 10 tons. Jumbo, P.T. Barnum fame, only 6 tons. They're very tall, but elephants are also very slender. Mastodons, they're not. They pack on the pounds. If you look at them from the top down, they're very big-butted animals. Columbian mammoths, we often think of mammoths. The biggest one we have on record is about 12.5 tons. The biggest mastodon before this was one that I curated at the Illinois State Museum. It's from western Missouri, about 11 tons. We have to go all the way to Greece before we get to a mastodon that is about 16 tons. So this is definitely the largest elephant, the largest mastodon, mammoth, gomphothere, largest land mammal probably in North America, in the fossil record or in the modern record. So if you want to really think about it in terms of something that you see every day, it's really more like this. It's about the same tonnage and about the same height as a Bluebird school bus. You might have to chop off a little bit of the back end to make it fit really nicely, but that's about the size and the shape of the animal that we're talking about. So, kind of thinking about other things to compare it to. These mastodons from Greece. These are things that a couple of years ago I had the opportunity to go over there. This is northern Greece, and I had the opportunity to look at that. These are Guinness Book of World Record holders. Not because they're the largest land animals, but because they have the longest tusks. So these are 15-foot long tusks, 16-foot long tusks. The tusks on our animal are probably not going to be that long. They'll be a little bit shorter, but not a whole lot shorter. They're still pretty long. We're looking at 12, 13 feet. But they also have, this is their lower jaw. It's just a massive lower jaw. Very, very heavy. They're about the same age as our animals, a little bit younger. But if we want to think about mastodons and who our mastodon is, a lot of times we have to zoom out to this global level. This is the cranium, the skull of our mastodon before we really started prepping it out. So it's gotten a little further along in the last couple of months as Sean has really taken a crack at it, but you can see it has kind of a long, low projecting face, long slender tusks. Let's see, this would be our American mastodon that is only 12,000 years old. We have hundreds of these across North America. You can see it kind of has a shorter face. We call it brevi-rostring. So brevi for short, rostring for face. And our animal seems to be a little bit longer, even though it has the same kind of teeth. This is its lower jaw. It's got this long, extended lower jaw, these very massive lower chin tusks. So we don't normally think of elephants as having chin tusks, but ours really do. We really have to go a long ways away to find something that's kind of similar. This is one from Saskatchewan. It's really the only North American jaw that I've seen that really looks like our mastodon. So when we go back, we were thinking about how this fits into the story of mastodons in North America. These are the two species that we often are thinking about. This is Zygolophodon or Myomastodon, and this is our American mastodon. And they both have kind of, they're very different. This guy has these tusks that are actually downward facing. It's got long, kind of lower tusks. It's got kind of strange teeth. Our American mastodon has normal teeth, but it's got this kind of shrunken face. And so they're very, very different kinds of animals. And our gray fossil site animal actually has characteristics of both, which is kind of interesting. These are some of the teeth that we look at. We can age these teeth. So we can look at modern elephants and say, okay, we know that this animal is 20 years old, and this is the amount of wear that it has on its teeth. And we can use that same kind of idea to age our teeth of mastodons at the Great Fossil Site. This is Ernie, and we think that he's probably around 30 years old. AEY stands for African elephant years. So 28 to 32 years old based on the wear of his teeth. We have another mastodon from there too that we call the red skull. And he's only represented by teeth because he's high enough in the section that all of his bones have dissolved away. And he's a little bit younger. He's probably in his mid-20s. But what are we doing with this? I mean, in addition to thinking about the science behind it, how mastodons may have evolved, thinking about their place in the local ecosystem, that sort of thing, we're also playing with new technologies like 3D scanning. And so we've got a couple of these really nice light scanners that we can use to scan big specimens. And this is the mastodon jacket. This is the mastodon skull when it came out of the ground. It was in this large plaster jacket that we then opened up, and so you're basically looking at one crushed mastodon skull. This is 9.5 feet from one end to the other, so about from here to the wall. Very large, very heavy. We actually had to contract a towing company to get it out of the hole because we couldn't lift it. Our bobcat couldn't lift it. We couldn't drag it out, so we had to drag it out in some other way. So you know, when you do mastodons, you're always dealing with logistics. But one of the nice things is with these scanners is we can start visualizing these specimens in different ways. This is a 3D scan that I kind of just animated last night and inserted in here. This is a scan of our jaw, so you can experience it in a way. You can zoom in, you can spin it around. The fun thing about this is we don't know how it will be used. As a paleontologist, this is really valuable because I can look at it and say, okay, I can document this particular specimen in a detail that I couldn't otherwise. It's like I'm there. So I can share this with someone halfway around the world and say, have you ever seen anything like this? But we can also upload it online so it can be used in different ways. We can use it in museum exhibits. We can use it in augmented reality or virtual reality applications. I was watching Empire Strikes Back with my son a couple of weeks ago, and as Luke Skywalker is hanging from an ice cave on Hoth, the camera pans and there's a mammoth jaw lodged in the wall. So some Hollywood producer said, I really like the look and the feel of a mammoth skull, let's put it onto an alien planet and incorporate it into a blockbuster movie. That's not anything I would ever imagine would happen. I have no control over that. But video game designers, virtual reality producers, educators, all these people, if you put this in a place where they can access it and you give them access, they can use it, and they can use it for good. That's what we want. We want our collections to be digitized, but then we also want them to be used in ways that we didn't really know that they could be used in. So that's one of the things that we'll be doing. This particular specimen will also be 3D printed for some of our new exhibits that are showing up this summer. So kids will be able to actually go up and feel what these tusks look like and look at those teeth up front, up close, and that sort of thing. So from a paleontological point of view, we can start treating these. 3D gives us the opportunity to think about these things as like topography. So these are two mastodon teeth that we have 3D scanned. This is one from Illinois, a late Pleistocene one. This is one of our Great Fossil Site teeth. We can compare these in really robust ways. The red here means that they're very different between the two teeth. The green means they're fairly similar. The blue means that there's something else going on. So we can create some of these really, really comprehensive analyses that compare things back and forth. I'm going to kind of close up a little bit here and think about what this elephant means in terms of the global context. There's been a lot of work on mammoths, mastodons, and Eurasian elephants actually in the last couple of years, and particularly looking at their ancient genetics. So we can get DNA out of a lot of fossil specimens. We can't get them out of gray fossil specimens because we're just a little bit too old. The top end for being able to preserve DNA is about 1 million years, and so we're just 4 million years too old. But there's a lot we can do with the things that have preserved in the last million years. And so one of the things that we're finding is that shape, I talk a lot about the shape of the jaw, the shape of the teeth, that sort of thing. And that's the bread and butter of what paleontologists do. We look at changes in shape through time. And who is like, another specimen. And we're finding that shape doesn't always correspond to evolutionary history. We're finding that, for instance, there's the fossil, a very large Eurasian elephant that we always thought was very closely related to African elephants. Actually, because of its DNA, we know it to be much more closely related. Actually, we thought it was more related to Asian elephants. But because of its DNA, we know it's very closely related to forest elephants in Africa. And so it looks like something that it isn't. Same thing with mammoths. This is a project that I'm just kind of throwing a whole bunch of data up there, but it's to remind me to tell you about something. I worked on a project with mammoths for many years, and it was something where we used to think that we had 4 species of mammoths in North America. We had woolly mammoths, we had Columbian mammoths, we had a species called Jeffersonian mammoths, and then we had pygmy mammoths, which are off the coast of California on some of the Channel Islands. They were very small. At their adult height, they would be about this high, so they're very, very cute. And so we would call those different species. A couple of years ago, I worked with a PhD student at McMaster University in Canada, and he started sampling all these things with the idea that he just wanted to know how different are these different species genetically. And what he found was that they aren't different at all. In fact, they aren't even different at the subspecies level. So even the pygmy mammoths could interbreed with the biggest Columbian mammoths. Their genetics were so similar across North America that we were very, very surprised. So you can end up with a lot of shape variation and not very much genetic variation. And so it makes me very hesitant to say that our great fossil site animal is a new species. It makes me hesitant to say this one is way outside of normal for all elephants everywhere because they're so variable. And which makes them a lot of fun to study. It also makes them really messy to make sense of. So in the future, we still have a lot of work left to do. We have, most of the animal is out of the ground. We still have where we think the backbone is. We have some ribs, but other than that, a lot of the animal's out of the ground. But it's going to take some time to clean those specimens up, to glue them back together, and to stabilize them and get them ready for analysis. Part of that is what I've been talking about is how does Ernie, how do these great fossil site mastodons fit into the story of elephants on a global scale? Because if they really do have something to say at that scale, we're not just talking about North America, we're talking about the world as a whole. And it is a really interesting story. But then the other thing that we've started talking about, and we've been talking about it ever since we started, we found this mastodon, is we need to have it on display somewhere. But there's a caveat. We're talking about a really, really big animal. And so the idea of getting it, mounting it in our lobby, for instance, is actually pretty, a lot of you have probably seen our lobby. It's good size, but it's still not going to fit a mastodon. So we're thinking about other ways that we can do this. We've been talking to the big 3D printing lab down in Oak Ridge National Labs that prints cars and RVs and things like that. They do this oversized printing stuff, and they've expressed interest in printing a mount for us, and so we're working with them. Most museums, if they have something, we may be thinking about something outside, in which case we have to think about making it weatherproof. Most museums, if they're putting something outside, it's going to be a bronze. This may be the largest bronze I've ever seen. Which adds up in dollar signs in my head. So these are the direction that we're going, and kind of where this mastodon is going to be. You will see it. I guarantee you will see it. But it may take some time and some creativity to figure out kind of where and how you see it. But that's all I have for today. This is a series. We have a lot of volunteers. It's a mastodon, so everybody is involved. Our volunteers are key, and even some of the paleontologists and the staff at the Great Fossil Site. We're all working on it together. Even though I'm the specialist, I can't do it without those people. So that's all I have today. If you guys have any questions, I'm happy to answer them.
Did Ernie have the articulated? Was he a ballet dancer, Ernie? Did he have articulated ankle, Ernie?
Did he have so the question is, did he have articulated ankles?
Ernie, yeah.
Yeah, he did. So in most of our ankles are articulated. Now I think about it. So not only do we have the front wrist of the front right leg that's articulated, that I was talking about, that we got CT scan, but there are parts of the back leg too, back foot.
He walked on his toes.
Yep, walks on his toes.
Ballet.
Yeah, twinkle toes.
Kind of big.
16.
Dr. Chris, don't forget the
Oh.
Hoyo Negro.
Right, so Ray is reminding me. So one of the directions that we're going, you may have seen some news, my colleague Blaine Schubert has been working in the Yucatan at a site called Hoyo Negro. And if you subscribe to National Geographic, and you have just subscribed for the last year or two, you probably saw there was an issue, maybe even 2 issues, that featured Hoyo Negro. Hoyo Negro is a underwater cave just north of Tulum in the Yucatan. And it's one that there's actually many of us that are involved. I went down last November, and we and helped them out. Since it's an underwater cave, it's highly technical diving to get down to the bottom. The cave itself is about 120 feet deep, and you have to dive into a side passage, dive through that side passage, and then down the Hoyo Negro, which is Spanish for black hole. At the bottom and around the sides, there are all kinds of Ice Age animals. So there are short-faced bears, saber-toothed cats, gomphotheres. So we talked about gomphotheres. There are gomphotheres in the passage. So this is a cave that's large enough for a lot of these animals to come in. So think about a cave that's large enough for an elephant to walk through. But this is also a really interesting cave because we have one of the earliest human skeletons in North America. And we call her Naya. She's been named. She's about 12,000 years old, and she is very complete. The analysis on that has really is kind of tidying up. It's finishing up. Most of her has already been published in the journal Science, but there are some little bits and pieces that are still kind of coming out. Our involvement, and the involvement of the person who kind of took the lead on that, his name is Jim Chatters, and he's a bioarchaeologist from Washington. And he's looking to kind of hand over the reins of the Hoyo Negro analysis to people that can deal with the non-human animals, deal with the saber-toothed cats and the short-faced bears and that sort of thing. And he approached Blaine about being involved. Blaine said yes. And the reason he said yes is, well, number one, it's a really neat site, and it's very, you see the imagery is these divers, pulling up these beautiful bones out of an underwater cave. But also because it's a similar setting, paleontologically and geologically, to what we probably have at Gray. So what we may have at Gray is like I said, a sinkhole that's been flooded. But then if you think about sinkholes, a lot of times the edges are really dynamic. So they're constantly eroding in. If they're rocky edges, then they're falling in, that sort of thing. And so one of the things that we see as an analog are some of the cenotes in Mexico. And so working in Hoyo Negro helps us understand what is going on at Gray. It helps us to understand how those animals ended up there. Helps us to understand some of the biological and chemical processes that are acting on those bones as they're in the ground. And so it's a really interesting project, and it does tie in. And so one of the things that we think of with, a lot of people ask, well, how did these mastodons end up in the sinkhole. And one of the neat things about it is that these bones are they're surrounded by big, huge boulders. And there's not a whole lot of dirt in between the boulders and the bones. And so what we think is going on, at least our working hypothesis, is that they entered the sinkhole as part of a rockfall event. So not only do we have our biggest mastodon, Ernie, kind of laid out and articulated in this big hole, but we have the remains of 4 other mastodons very close by. They just aren't as well preserved. So you have a 16-ton animal and then potentially other multi-ton animals, all within a very constrained area, all with a jumble of big boulders and rocks. And so our the logical jump is that they were kind of crouching up to the edge of the sinkhole, up to one of these dynamic edges that may have been undercut, and then all that weight would have caused a rock slide. So that's something that we can look at, cenotes, we can look at some of these flooded cave complexes in Mexico and in the Yucatan and say, okay, what are the processes that would have affected animals at the Great Fossil Site? How do rock falls look in these other cenotes, in this other context? And when you kind of zoom out to that comparative level, that's when you start learning about things.
You think they got in this hole, just fell in, and then couldn't walk back out?
That's possible. So one of the neat things about gray, that's definitely true of Hoya Negro, because what we have there is the sea level is much lower during the Ice Age because a lot of the Earth's water is locked up in glacial ice, and so we actually have it's 120 feet lower than it is today. And so what we think is happening down there is that these caves are exposed and they're above sea level. And it's also very dry. We don't think of the Yucatan Peninsula as very dry, but if we look at the plants that are there, there's a lot of cacti, a lot of succulents, a lot of things that are adapted to dry landscapes. And so, and that's part of the geology. It rains a lot, but the rain comes down and it immediately goes through the cracks into these underground cave systems. And so what we think is going on there is that you had these large caves that smelled wet. And so when you had a dry period, elephants, saber-toothed cats, people, they know where the water is. And they know that if they go into this cave, they will probably find it. And in this case, they went into the cave, they went into the side passage, and they weren't able to see the deep vertical shaft that is Hoya Negro deeper into the cave and fell in. And so it was definitely a trap in that respect. At Gray, it's more complicated. I mean, everything is more complicated at Gray. Job security. But it's more complicated. It's open for thousands of years. It's not strictly a cave. And so you probably have these edges that are they change very rapidly. So you may have a rock fall over here this year, but then that stabilizes that edge. It creates more erosion over here, or it creates another high edge over here, and so then that rock, and so you may have this in a sinkhole, it may be that you have different things going on at different times. And so accessibility may be an issue. With our tapirs, so many of you probably know, we also have, it's rare that I don't mention this until this point in the talk, but our museum has more tapirs than any other museum in the world. I think we can probably say that with pretty good confidence. We have at least 200 tapirs from the Great Fossil Site. These are all an extinct dwarf tapir, and they're everywhere. Even among the mastodon bones, we see tapir bones. And we can do things when you have that kind of a sample size, when you have that many numbers. You can do things, you can understand their biology in a way that you can't otherwise. So we can look at 100 tapirs and say, look at the wear on their teeth and the eruption patterns on their teeth and get at their ages. Then we could say, okay, how many really old tapirs do we have? How many middle-aged tapirs do we have? Now, how many baby tapirs do we have? And then we could say, are there biases? Do we see more young and old, which is be expected if they're just going in there because they feel sick or something like that and they're dying that way. But we don't. We actually see an even representation of tapirs across those age groups. So we're not quite sure, we think that tapirs just like water. We know that modern tapirs do. And so it may just be that that's where they were, that's where they died. Some of them may have died, kind of catastrophic violent deaths because they were chomped on by alligators. Some of them may have died because they were sick or old. So, there's a lot of different ways that these animals can make it in, and not always the same way. Certainly a grave.
When did they become extinct, mastodons?
When did mastodons come extinct?
Yes.
Funny you should ask. We did, when I was in Illinois, we did it was a 5-year project where I visited, 50 different museums throughout the Midwest and inventoried each one of their collections. We added about 600 mastodon localities to the record and dated them. So I can tell you it is about 10,900 years ago in radiocarbon years, which actually comes out to about 12,700 years in calendar years. That doesn't mean a whole lot, unless you also know the other part of the story. So climate change at that time, we're going from really, really cold glacial conditions about 18,000 years ago. It's slowly warming up, slowly getting more wet, more moist. And then about the same time that mastodons go extinct, there's a swing back towards getting very cold. So that's part of what has always been a big debate, is what is driving mammoths, mastodons, a lot of these other Ice Age animals extinct? Is it climate change, this swing back towards glacial conditions that just can't adjust that quickly? Or it also happens to coincide with when we think that humans are really expanding across the continent. And we know that people have a pretty big impact on their environment. At this time, those human groups really weren't very big. We think that they were probably eating a lot of meat, they were probably eating a lot of animals. However, I kind of land on the side of I'm not sure that they're capable at that time of really eliminating entire species. For our purposes in the Midwest, we saw some really interesting patterns in how they went extinct. Mastodons, 600 years before they go extinct, are actually probably at the biggest populations that you see anytime in the last 100,000 years. Their population actually seems to be growing. And one of the reasons that we think that is because the big predators like saber-toothed cats and direwolves go extinct first. So then you have mastodon populations that are starting to yo-yo kind of out of control. So you have mastodon populations expanding and then dying off because of kind of sickness or starvation or other things. And so their populations crash. And we see that in caribou today, we see that in deer today, we see that in other species. But then at some point, about 12,700 years ago, they crash and they stay gone. So, there's an increased resolution to our understanding of their extinction too, that we're just getting at because we have kind of new techniques to date them very, very well.
Chris, thank you. If we have other questions, he'll stay around for it. And this was just a great program, and we're going to have that. And I want you to turn your tests in as you leave. It's more than we can fathom, I'm sure. I'm just fascinated by the whole thing. And thanks, everybody.